Yeah, thank you very much, Changjing, for this kind introduction, and of course, first of all, for the invitation to speak in your seminar. Yeah, it's a great pleasure for me. It has been some time ago that I was visiting Shanghai, and I would love to be there again. But let's use the occasion to have this online seminar now, and where I can talk about a recent result that we achieved with the nuclear clock isomer Scandium 45, and making use of the most brilliant source of X-rays in the world, the European free electron laser in Hamburg or near Hamburg. So this should be actually the recent publication. The title should be the agenda for today. It's basically everything well represented in the title where I'm going to talk about. So the first aspect will be a short feature about clocks, especially nuclear clocks and the history of their development. And then I will introduce also the nuclear isomer Scandium 45, which is not at all so exotic. All the scandium that we use and for whatever purposes is scandium 45. So it's a very abundant isotope. Then I will explain to you how we managed to resonantly excite a particular nuclear resonance of this isotope. And these are the main topics in my agenda today. So as I promised, I will talk about clocks a little bit in the beginning to motivate the content of this presentation. So the measurement of time, it's basically maybe one of the first scientific activities of humankind that was striving for increasing precision in the measurement of time over the decades since the first inception. So ranging from the observation of periodic celestial motions. So this was, of course, the first instance of a time signal, a periodic motion. Yeah, and what else is there? The most obvious periodic motion is the periodic set of the sun and moon and stellar objects that the early humans could observe and use that as a measurement of time. However, with the evolution of mankind, then of course other means for measurement of time came online, so to say, were invented. First of all, mechanical clocks, that of course offer a much higher precision than celestial bodies, as we all know, mechanical clocks, and then much later, of course, also solid state-based watches like these wrist watches that we all know and are still in use. So you see in the bottom, you see the respective fractional uncertainty of these time measurement devices that already increased over several centuries. And this was actually getting a much quicker pace then towards extremely high accuracies when the first atomic clocks were invented. So we all know the famous cesium fountain clock that nowadays provides the definition of the second as a fundamental unit of time in international standards. And also the cesium clock, I mean, you see here the blue line is the further development of the cesium or atomic fountain clocks here towards fractional uncertainties in the range of 10 to the minus 15. And some of these clocks or variants of these clocks are nowadays traveling on satellites around the Earth to constitute our global positioning systems. And there might be the evolution is ongoing to enhanced accuracies with clocks that are based on optical lattices, where charged ions, particular ions, are trapped in deep potentials, and then probed with optical means, laser radiation. Here we are actually at a level of accuracy of 10 to the minus 18 with the strontium 87 clock, which actually corresponds to a uncertainty or deviation of the reading of the clock of 1 second in the age of the universe. So this is a remarkable accuracy that certainly goes beyond what is meaningful in practical everyday applications. But here we are entering a regime where applications are in extreme metrology to probe, for example, the potential variations of fundamental constants as they are predicted by certain cosmological models. And this is a driving force towards increasing accuracies to probe tiny, very tiny, extremely tiny changes of the environment, to probe relativistic theory assumptions like gravitational redshift or the equivalence principle to highest accuracies to challenge actually the assumptions of relativity theory, for example. So in this respect, nuclei come on stage because they might offer even higher accuracies than the currently available atomic and optical clocks. So, and that constitutes the subject of my presentation today, to give you an account on a new candidate on this stage, namely Scandium 45. But before I come closer to that, I want to give you an account of what is available today. So I just showed the temporal evolution of the development of clocks. Here is actually a map of some isotopes and atomic transitions that qualify for high precision clocks, here shown as a function of the natural line width of the transition that is always involved. So the basis for atomic or nuclear clock is always a ultra narrow atomic or even nuclear level that provides a reference, a very stable reference to which then any optical signal or optical clockwork could then be related to by frequency combs or something. So we have here the other axis, the vertical axis, is the transition energy. And we have here various regimes. Here's the optical regime, also with the famous thorium-229 isotope that I will feature a little bit on one of the next slides. And we have here the ion clock transitions that I have just shown you on the previous slide. But if we go up here, we enter the regime of soft X-rays, where there are isotopes that belong to the class of Mössbauer isotopes. That's actually, there are not so many in the soft X-ray regime. There are more in the regime of hard X-rays extending from, say, 6 to 100 kiloelectron volt transition energy. And here, for example, we have the most widespread used Mössbauer isotope iron-57, which has been serving as one of the first isotopes or nuclear transitions for the use in metrology of relativistic effects. So the first gravitational redshift experiment was, as you know, done by Pound and Repka on using the iron-57 Mössbauer isotope. It was then later there was another isotope, zinc-67, which is not here on this screen, that boosted actually the activity in using nuclei for high precision fundamental probing of relativity theory. So okay, so this is a bunch of Mössbauer isotopes that is also now used in material science to give an extremely sensitive reference to probe interactions, solid-state interactions of nuclei to probe actually solid-state properties. Yeah. So this is a widespread use of many hundred groups worldwide are using these isotopes in material science. But for ultra high or extreme metrology, we need to go further here to the left. So where actually these diagonal lines are parametrized according to the Q factor, the ratio of the transition energy over the natural line width. This gives the resonance quality factor Q, which is then given here in these values with five orders of magnitude separation. So, and here we have, for example, at the Q equal 10 to the 20 line, we have thorium 229, but we also have not far away from this scandium 45. And this will be the main actor here in this talk today. And yeah, I've mentioned these two here already. So let's move on. First, for putting this into perspective, this is the general scheme of an optical or nuclear clock. So you have either an atom with an electronic level, which is very narrow, or a nuclear system, an atomic nucleus, which is orders of magnitude smaller, of course, compared to the atomic diameter. But both are exhibiting levels, two-level systems with sufficiently narrow line widths to qualify for high and extreme accuracy applications. So these levels then are used as reference frequency for state detection or the fluorescence radiation or whatever nuclear or atomic decay product is then monitored for state detection, and frequency control with which a stable laser is then stabilized, which is then itself coupled to an optical clockwork, for example, a femtosecond laser to actually generate then via a frequency comb, for example, a time signal that can be read. So this is the very scheme of an atomic or nuclear clock that would be needed to be implemented in case that one even wants to use a nucleus actually for a time reference signal. So here is again a chart of the various transitions. So here are even more nuclear. These are all the nuclear isomers actually shown here. Again, atomic shell transitions shown here. These are the various ions that are considered and qualify. And we have here the Mesbauer isotopes, again with iron 57 here in this region. But we need to go further to the right to see scandium 45. And here I show this actually to explain you the values, the parameters that are relevant, of course, here. So the energy is 12.4 keV, the transition energy, which is almost exactly 1 angstrom wavelength. And the line width, the resonant line width is 1.4 femtoelectron volt. So this is 6 orders of magnitude smaller than the natural line width of iron 57. So we are entering really a new regime here compared to existing Mesbauer isotopes. And the scandium 45 is in principle the narrowest, the most narrow nuclear transition in the regime of hard X-rays. There might be others actually, like rhodium 103 or silver 109, which are, on the other hand, orders of magnitude higher, or orders of magnitude higher in transition energy, and also much more narrow in the frequency bandwidths or the natural line width, so that addressing these transitions would be extremely challenging. So scandium 45 is in a region that is reasonably accessible but not very easy. And I will explain you why and what challenges we had to manage to tackle to observe this resonance for the first time, excited from the ground state with X-ray laser radiation. Okay, so yeah, here is a list of nuclear resonances. Here is the criterion that the relative bandwidth should be smaller than that of iron 57. I mentioned some isotopes, of course, the scandium and thorium, the silver as well, to give you the detailed numbers here. So I told you that I will give a short account on the thorium-229. That is a nuclear isomer that is actively followed after since many decades for applications in as a nuclear clock, because the remarkable feature of the thorium is that the resonance energy, the transition energy, is 8.3 electron volt only. So that is the lowest lying nuclear level that is known to date. And this could be addressed within ultraviolet laser, for example, in principle. And that constitutes the driving force to use this isotope for applications in extreme metrology. So the Q factor is that is the inverse of this quantity is 10 to the 20. I mentioned this already. The natural lifetime is several hundred or thousand seconds. Even that is not known exactly. It depends on the ionization state in which this nucleus is in. So there is a huge lot of publications that have appeared in the past years and decades. I have listed just a few of the most recent ones. So the progress is accelerating in principle. You see more and more publications in high-profile journals, and it might not be so far away from today that there will be an atomic clock or nuclear clock based on thorium-229. With using nuclei, of course, there are a few aspects that are worth to be considered, because nuclei offer some advantages, significant advantages over atomic resonances, and those I have listed here to motivate actually why it is worth to look into nuclei. So first of all, yeah, we have higher Q factors. I just mentioned scandium and thorium as two examples. That would be one reason. Then, of course, the higher frequency, especially that of scandium-45, offers a greater stability just for simple statistical reasons, because this higher frequency means a shorter period of the carrier frequency, so that fluctuations from external sources are averaged over more cycles than in the optical regime. So this gives a greater stability and accuracy from that simple reason. Then, due to the smallness of the nucleus, the geometrical size of the nucleus compared to the electron shell, the nucleus is much less sensitive to ambient electromagnetic fields as compared to what electrons are in atomic orbitals. Yeah, so there are much more effects that limit the accuracy of atomic clocks, and that requires more shielding or corrections to be made to account for fundamental effects like the shift of the transition frequency just by thermal radiation and so on, and many more of such effects where nuclei are much less susceptible to. Another advantage is that a greater number of atoms can be used if you use the nuclei of the atom. So in principle, we can use scandium and also thorium in a solid state matrix, and we don't need, say, optical lattices or traps to have clock atoms well separated in a dilute gas or in iron crystals. at low temperatures to control their mutual interaction. So if you have nuclei embedded in a crystalline lattice, this is actually a natural natural lattice, like in a lattice clock, or a laser-generated optical lattice, which also can yield very deep potentials. But yeah, the crystalline lattice with the strong binding forces naturally gives you a lattice to stabilize the position of the nuclei that are supposed to be the frequency references. Yeah, and then we have the Mössbauer effect, of course, that comes about due to the deep potential in which the nuclei are bound in a solid, and it also allows one to prepare a huge amount, whatever, 10 to the 10 or more nuclei in a solid, which can be prepared all identical, and the huge number of these nuclei automatically leads to a much higher stability and accuracy compared to a single ion in a trap or a few ions in an optical lattice, for simple statistical reasons. And you can also use moderately low temperatures if you use Mössbauer nuclei in a solid state environment. Okay, so these are a number of advantages that come into play if you use nuclei. However, I mean, it's still not trivial, as we will see, to make this work. And now I want to focus here on the scandium-45 as a candidate, not too far away regarding this value here from the thorium-229, but at an energy that is much higher, where we have nowadays radiation sources, X-ray lasers. At least they are called X-ray lasers. They are not true lasers like optical lasers are, but they offer high intense beams that allow us to address this very narrow level, as we will see. And the lifetime is in the regime of half a second, roughly. So that is also very convenient for time-resolved detection techniques. And the greatest advantage is this 100% natural abundance. So we don't need complicated enrichment procedures to get this material. We just buy it from a chemical or metal store for chemicals, and you can handle this in principle in a machine shop. However, there are some requirements that then need to be taken into account if one wants to really go to this value here. I come back to that later. So the fact that scandium-45 is coming on stage only now is the fact that there is no convenient radioactive source available that could qualify for doing conventional Mössbauer measurements. Yeah, so there's the branching ratio of any possible parent isotope to populate this 12.4 keV level. The branching ratio is so small, 10 to the minus 8 or lower, that there's no possibility to produce a reasonable radioactive source for doing Mössbauer measurements. Otherwise, it might have been done already since a long time. But we have other sources that allow us to access this level by exciting this from the ground state. Yeah, not populating this from a higher state of a parent isotope that is populated in nuclear decay, but using X-ray sources, accelerator-driven X-ray sources like synchrotrons or lasers, we have the chance to excite this 12.4 keV level from the ground state. And these attractive properties I mentioned already. And let's have a look what sources are available. and how we can get them into work. So that is the roadmap now. That is actually an idea that was already worked out by Yuri Shvitko and Gena Smirnov more than 30 years ago, that the resonant excitation of scandium-45 using hard X-rays from accelerator-based sources. And this was published in this work here, where they came up already with some reasonable count rate or estimates for the brilliance and the spectral flux needed actually to generate a reasonable signal from scandium-45. So since then, I mean, since this work, you see all the parameters that I've mentioned. Since this work, there were 2 attempts to look at the scandium-45 at third-generation synchrotron sources. They were so far unsuccessful simply because the spectral brightness was too low. But in the meantime, considerations went on, actually, what interesting science one can do with this resonance. So when there was the scientific case for the European XFEL at that time in 2000, still called the Tesla XFEL, because it was part of a large linear accelerator that was planned near Hamburg. And this was a contribution from Yuri Shvitko to a workshop on nuclear resonance scattering, potential nuclear resonance scattering experiments at the XFEL that was planned near Hamburg. And here you see again the scandium parameters and an interesting application, namely what actually is obvious. It was obvious right after the discovery of the Mössbauer effect to use this ultra-sharp resonance line for gravitational redshift experiments. This is, of course, here also possible under much different conditions, because in the Pound-Repka experiment, the height in the gravitational potential that was used there was 22.5 meters. With the ultra-narrow resonance of the scandium-45, you can decrease this height to a millimeter or below. So you can probe gravitational redshift on much smaller length scales, that are not accessible yet to probe gravitational effects and test, for example, and put new boundaries, for example, or challenge the equivalence principle of relativity theory to scales where it has not been probed yet. So this is a potential application. So here actually what is shown here is the level shift of the scandium levels of the scandium resonance energy when the photon or the photon energy that is changing upon traveling along the gravitational potential of 1 millimeter. So this would be then corresponding to 2 shifted resonances on the energy scale. At the synchrotron, as what we are doing in the synchrotron, we convert these when we excite hyperfine split levels at the synchrotron, we convert this the energy spectrum into a temporal pattern simply by experimentally Fourier transforming this, and the split line would then on the time scale correspond to a beating that one then would observe as an indication of the gravitational redshift in such a setting here, where we have 2 scandium foils on different gravitational potentials and a monochromator in between to transversely displace the photon beam. And here, this would be then the signature, actually, this temporal beating from the beating period. You would then be able to get back the energy difference, that corresponds to the height and the apparent weight of the photon, actually, that you can probe in this fashion with it. Yeah, so that is one application that one can think of once such an ultra-narrow resonance is available. And now I want to come closer to our experiment that we did about a year ago, or slightly more than a year ago, at the European XFEL. Here again are the parameters. Here is actually now the level diagram in more detail. So we have a 12.4 keV level of the scandium, and we pump this level here with photons from the laser, and the decay can proceed over different channels, either, of course, the completely radiative decay by 12.4 keV radiation, but the more likely decay channel is the internal conversion, IC mentioned here, which is 99% or more of all decays proceeding through this non-radiative channel, where the nucleus, the excitation energy of the nucleus is then transferred to an inner electron of an inner shell, the K shell of the electron shell, and that's great. Those are these electrons that have a finite probability amplitude at the nucleus that then are susceptible to take away the energy by this internal conversion decay, where a proton captures an electron and converts into a neutron, and the remaining hole in the inner shell, electron shell, is then filled by electrons from the upper shells, leading to K alpha and K beta, dominantly fluorescence radiation. And that is the decay channel that we are going to detect. That is the idea. And what is here written on the right, I have mentioned already. So, but here for the remainder of or for the coming slides, it's important to know that we are for the first experiment, we decided to detect this fluorescence radiation, which has an energy of about 4 kilo electron volt. So that is one aspect. Then the question, why using the European XFEL? That is actually a unique accelerator-driven laser source right now, although there are many more in the world meanwhile, and many more are coming online soon. However, the European XFEL is especially suited due to its high energy and its superconducting accelerator technology to radiate in the hard X-ray regime, to set also up a seeding scheme where the radiation through the generated in the chain of undulators is amplified even more. There is a high rep rate available that gives a high number of pulses with high pulse energy, for especially suited for generating a high spectral flux that is principal factor of up to 1,000 larger than those of conventional synchronous radiation sources that are available these days. So the European XFEL is basically the first high repetition rate X-ray free electron laser with a bunch spacing of about 200 or 400 nanoseconds. So the temporal pulse sequence of this particular mode where the European XFEL is running is shown here. So the standard mode are bunch trains with a user-defined number of bunches that can be up to 300, 400, or in the later stages, maybe even 2,800. Separated by 100 milliseconds. So the intrinsic repetition rate of these bunch trains is 10 hertz. And and you see already that this time structure is ideally suited for the detection of the scandium resonance. because from the perspective of the lifetime of the scandium, these pulse trains, these trains of many short time separated pulses appears as a single bunch, which with a duration that is much shorter than the lifetime of the scandium resonance. So that's typically, even if you have 100 bunches with a separation of 200 nanoseconds, you are below 1 millisecond in total length here. And then you have 100 milliseconds or slightly less than 100 milliseconds time to where no excitation occurs. In that time, you can look for the delayed nuclear fluorescence or these 4 keV fluorescence photons emitted from the scandium nuclei. So this is this time structure is really suited for this resonance. And it was only a few years ago that this so-called hard X-ray self-seeding mode, I will show that later, became available. That gives you an order of magnitude more spectral flux, as shown here in this line, compared to the conventional SASE self-amplified spontaneous emission principle that is the standard operation of these standard mechanism of radiation generation of these X-ray laser sources. Here's the experimental setup, and here it's a bit more illustrated how this hard X-ray self-seeding works. That was also crucial, actually, to reach the critical spectral photon flux that we estimated to be needed for the detection of the scandium resonance. So this works in a way that that within the undulator section of the X-ray laser, between two undulators, there is a space for crystalline reflection. The crystalline reflection basically sorts out or selects a certain mode of the SASE radiation, a certain spike actually here of the SASE radiation. I hope you can see it here. So the normal operation is that the radiation generated in such a SASE process is based on amplification of radiation that generates itself from noise of the electromagnetic field in the undulator. So it's a quite spiky actually pattern that varies from pulse to pulse. And so this pulse is maybe 100 femtosecond long here, and the spikes here are only a few femtoseconds. So if you put a crystal here inside, you would be able to select out of this relatively broad energy band a single spike and use this actually then for further amplification. So in principle, you use the radiation or what is left over, and that is actually a hole in the spectrum. But for the amplification process, that doesn't matter if the bunch overlaps with the wake of the delayed wake of this radiation transmitted to this Bragg reflection Bragg crystal. Then you are effectively able to amplify a single spike of this noisy pattern here, and continue to amplify it in the further section of the undulator sequence here. So of course, this is what we use. This leads to pulse widths of about 1 electron volt or even less, maybe, of the desired energy. And so this is the radiation source here. And then we have here the scandium-45 sample with the resonance detection unit. And this is the trick here that we applied. I have the animation here below. So we have here this foil, and we move the foil in and out of the beam. It's in the beam for being excited, and then we move it within 10, 20 milliseconds into the place between two detectors where we cover a rather large solid angle to detect the 4 keV fluorescence photons. So this is possible with a fast mechanical shutter. on which this scandium foil is mounted. And this is shown here in this animation. So you have the bunch train coming from the left now, exciting the resonance. Quickly, the sample is moved between the two detector telescopes here of these solid-state drift detectors, and this is periodically repeated with a rep rate of 10 hertz to actually reach a detection condition which is extremely low noise. So we have a strong shielding here of the detectors from the very strong incident beam. We have a motion of about 12 millimeters far away from the position of the incident beam. And we have intrinsically low noise detectors. These silicon drift detectors are low noise. They have an excellent energy resolution so that we could select the 4 keV resonance fluorescence radiation with a high signal to noise ratio and separate them from all parasitic photons that might have been entering the detectors at the same time. So this is the detector, the shutter unit here. That was a simply laser shutter from Thorlabs that we modified for this operation here. And here are the silicon drift detectors that we used that were covering a rather good solid angle around the sample. And last but not least, of course, that is what I mentioned already. Here on the right side is the section where we measure the photon energy. So once we had found the resonance, it was, of course, the next important step was to measure the resonance energy. So the resonance energy was known before only to an accuracy of plus minus 50 electron volt. That is a really lousy accuracy. So we were aiming at a much higher accuracy, of course, as an important requisite for any further applications. So you need an exact value of the resonance energy. And for that purposes, we used two crystal spectrometers, one for quick monitoring of the relative energy, and then a high resolution crystal for applying the bond method. In the bond method, you measure two reflections of a perfect single crystal, and from the angular separation of the two Bragg reflections and the known lattice constant of the silicon, one can determine the absolute energy of the photons with a very high accuracy. That was the key, actually, to the main result of our experiment. I should also mention that the heat load of the radiation is, of course, an issue. So we haven't used any monochromator in between. We used a direct beam from the undulators of the free electron laser. We widened the beam up. We distributed the heat load over a sufficiently large area so that we were below the limit, the critical limit for melting the sample. But that was, of course, an important aspect as well. Okay, this is basically the experimental setup, and that we used at the European XFEL, and this is the data. So what is shown here? So we have orange and blue spots here. Every spot is a single photon detected and parameterized or sorted after incident energy of the incoming photons and the detector energy. So the AMTEC detectors are energy resolving detectors, and with a very good energy resolution. So that is the energy range that they cover from, say, 1 kiloelectron volt up to 25 kiloelectron volt. And so here you see all the events that we recorded, and there are interesting regions. So you can imagine that this here, the zero here in this graph is already the center. Here is the very resonance. I give the value later here. But here you see, actually, if we enlarge this region here, you see two accumulations of detection events that are matching with the energies 4.01 keV and 4.45 keV for K alpha and K beta fluorescence photons. So that is a clear proof that indeed the nuclear resonance was excited. And this was actually, all these photons were already time gated. So the detector were switched on only 20 milliseconds after the excitation pulse came, so that we only recorded the afterglow, so to say, the delayed luminescence or fluorescence, one should better say, of the scandium atoms after excitation. So this contributed also to this very high signal-to-noise ratio that we achieved here. And so this is what I mentioned already, these clusters, that is the direct confirmation of the detection. Then we have looked here also at the 12.4 keV section here, but there was no statistically significant emission. So that would be the elastic nuclear fluorescence or forward scattering that we would expect to see here, but the experimental conditions were not optimized in that stage for detection of those photons. So also theoretical simulations indicate that we should have had a much thicker sample to observe this decay channel here. So everything is consistent with expectations. So this was ensured that we were really on resonance here in this situation. And yeah, and this is actually, if you integrate now here over this region here and plot the number of photon events as a function of this energy here. So the color code here is just between the two detectors actually. So the one was in forward direction, the one in backward direction. These are the signals from the two AMTEC detectors that we employed. Okay, so then integration over the detector energy range and plotting the histogram as a function of the incident photon energy gives you this resonance curve here, corresponding. Initially we had a large scan range. This was then confined to a ±4 electron volt, and in the experiment, in the whole measurement time, there were 10 to the 20 12.4 keV photons incident hitting on the target foil. And so in this respect, it's a remarkable signal-to-noise and ratio at a remarkable selection and discrimination capability of this experiment to record to be exact, 93, we counted them later, 93 4 keV fluorescence photons were detected here in this curve out of 10 to the 20. So this is a remarkable ratio that allowed us then, by carefully calibrating the photon energy, to determine the absolute resonance energy, which is given now by this value here. And so the literature value before was 12.4 ± 50 electron volt. Now we have 12.389.59 with these errors here given. And so this is a remarkable achievement that enables us for the next experiments to directly go to this energy and be sure that we are on resonance. So we actually improved some of the literature values of the scandium-45. Of course, first of all, the resonance energy as shown here, but also in comparing the numbers of the yield of fluorescent photons resulting from the internal conversion decay, we could actually get a refinement on the internal conversion coefficients here to those values for the total or the K alpha conversion efficiency or conversion coefficient. So these are the green shaded regions here where we have new numbers. We also got new numbers for the resonant cross section, which is still within the range. No, it's definitely larger than the literature value that was published before. So these are new parameters that are resulting from this work. And so there are interesting new next steps to be done or needed to be done So we have submitted a follow-up proposal. We want to look then for this coherent forward scattering channel, where actually this channel that I've shown at 12.4 kV, where we didn't see a signal yet. So because the conditions were not optimized. For optimization, we need actually a thicker foil. We need to cool down the sample to temperatures below 30 Kelvin to avoid line broadening due to the second order Doppler shift. And but then if this is successful and we estimate a relatively high count rate, at least a factor of 10 more than in the present experiment, then we can think about, for example, the first gravitational redshift experiments on millimeter or submillimeter scales, or to measure even extremely weak hyperfine couplings of the nuclei in a solid state environment, which hasn't been done before at all, and would open a new regime of studying hyperfine interactions. Yeah, so we want to improve the determination of the resonance energy even further. One order of magnitude should be possible with sufficiently well prepared X-ray optics. This would be also needed then to eventually develop a milli-eV monochromator for future experiments, a milli-eV bandwidth monochromator. And yeah, and of course, we also want to determine the lifetime of the single atom incoherent lifetime in the photonic decay channel, which is also not known yet, because so far all studies before our X-ray laser experiments, all the studies were made based on nuclear reactions where this scandium-45 was produced, where actually the excited state was populated by completely different decay channels and not by photonic excitation from the ground state. And this might be need to be addressed in another experiment to compare the lifetime measured in this decay channel compared to the existing measurements. Yeah, with this, I'm coming closer to the end, but I don't want to close without an outlook actually on the future. Of course, as you have seen with the European X-FEL, even with the brightest X-ray laser source in the world at the moment, at 12.4 keV, the count rate was still pretty low. I mean, 93 photons within 40 days of measurement time is not a lot. But of course, it was, as you saw, statistically very significant. But for future applications, one should have a source that is spectrally much brighter. And there is a candidate that is being researched on at the moment quite actively at many facilities. This is the X-ray free electron laser oscillator. And that is principle shown here in a sketch where actually an undulator is used for a periodic seeding of the photon beam. Periodic means that you use the radiation that is so the electron bunches are coming from here, so they are running through the undulator and then hitting a crystal that is part of a recirculation cavity. So the radiation then is guided through this pathway. There are other possibilities also possible, but this is the typical shape of a recirculation cavity as used in optical lasers as well. So that is actually used to feed in the radiation, the X-rays, again into the entrance of the undulator and use them for seeding again. So if they are coincident with the next electron bunch here, so the radiation is used to actually create micro bunching of the electron beams and amplify the photonic output even further. So the more the more repetitions here you have for the photons inside of this recirculation cavity, the higher the gain could be. And eventually, if you couple this out, you get an increase in brilliance, as shown here, that can be orders of magnitude higher than what is available here at present-day X-ray laser sources here. This is maybe a little bit optimistic, but that remains to be seen. These are calculations being made, but in any case, if such a facility would be available, it would actually boost the research on ultra-narrow nuclear resonances for extreme metrology applications. So a nuclear clock in the strict sense might still be many steps further away in the future, but nevertheless, on the way to the development of a nuclear clock, we will have then a source available to use scandium resonance, scandium-45 resonance for applications in extreme metrology. Yeah, and the nuclear clock, in principle, can be seen also as a high precision measurement device for time and energy. In principle, I mean, we will always be based on or rely on an accelerator-driven source, and we will certainly not be able to produce in the near future a compact atomic clock that can be mounted on a satellite and orbit the Earth to be a reference for the global positioning system or any other navigation system. But for earthbound extremely high metrology applications, this could be an extremely interesting isotope. So I don't want to close without mentioning my co-workers. So this was done in an international collaboration led by Yuri Schwitko from Argonne National Lab with me as a PI, Jörg Evers from Heidelberg, and Olga Kotarovskaya from Texas A&M University, and extremely motivated and active help of the technical and scientific personnel at DESY and at European XFEL was crucial actually for the success of this experiment. Preparing the experimental setup, the environment, and running the accelerators and the beamline, that was a really excellent team effort. Yeah, and this is then my summary with this picture here, which actually summarizes all the ingredient that we used. You see here a nucleus that is illuminated. You may guess it's a scandium-45 nucleus that is illuminated by the very bright light from an X-ray laser and excited. And eventually, the excitation energy is transferred to some electrons here in this cell. They are kicked out, and if the holes are then filled by other electrons, then we get the fluorescence radiation, which is not shown here. But anyway, I mean, it's here. The nucleus is drawn as a clockwork in principle, already anticipating the application of a clock, and the hands of this clock actually are not random, but they encode actually in the time that is displayed. They encode the resonance energy of the scandium 45 resonance. Yeah, and with this, I want to thank you very much for your attention, and thank you again for the invitation to your seminar.
Okay. Thank Professor Holzberg for this very impressive talk. So I think it's time for questions.
Yeah, I'm looking forward.
Dear Professor?
Yes.
Okay, I want to ask a question. What's the best method to excite the 229 TH?
That is 229 thorium, yeah.
Yeah. What's the best method to excite the isomer?
I didn't get the question exactly. I mean, you mean the way how to excite the thorium?
The way to excited the thorium. Yeah.
The thorium, I mean, that is still to be done. That it has not been achieved yet, at least not from the ground state, as we did. I mean, in this way, we are the first to excite such a small narrow band resonance from the ground state. For thorium, it has not been achieved yet because the resonance energy is not known yet to a sufficient precision to build a corresponding laser to address this resonance with sufficient high intensity. That is the current state of the art. The resonance energy is, they are making progress. They are narrowing down the bandwidth in which the exact resonance energy is expected. That's what I know. But the crucial point is actually the measurement of the exact transition energy. And then, also there's laser development going on at various institutes around the world. And it's also not very easy to design and commission and operate a laser at 150 nanometer wavelengths. That is what the energy would correspond to, because this radiation is highly absorbed in any material. And the efficiency of, say, a high harmonic generation or other mechanisms is not very high, what I was told. So, but I'm not an expert in this, but there are arguments actually that I mentioned that they make it difficult actually to find a source to excite this resonance directly. But colleagues are optimistic that they might be ready to reach this goal within the next few years, or maybe even sooner. I don't know.
Okay. Maybe you can use laser or electrons. Yeah. Some method is used to electron to excite the thorium.
I mean, so was it Bremsstrahlung?
Such as NEC or electron bridge.
With the electron bridge
Yeah.
transition. Yeah, so there were also considerations, but I'm not aware of any experimental progress in this.
I think until now there is no experiment.
Yeah, there's no. Yeah, that's what I know. Yeah.
Yeah.
Yeah. There is no experiment about the method. Yeah.
At least there's no result published yet. Maybe we don't know. Yeah. So Zhangxing, you worked on the electron bridge process as well, right, with Adriana?
Not too much.
Okay.
Yeah. But I think there is no experiment about this, especially for plutonium.
Yeah. That's yeah.
Okay. Do you have any other questions?
Thank you.
Thank you.
Actually, I have a question.
Yeah.
Yeah,
Please.
actually, I think someone will ask because the X-ray field is very large.
Yes.
I think maybe it's a disadvantage to build a clock based on X-ray field. It's too large. So how do you think about this?
Good question. Yeah. I mean, there are activities worldwide to use other mechanisms for generating hard X-ray, highly brilliant X-rays from other types of acceleration or particle acceleration mechanisms, like plasma wake field accelerators and so on, that can have much higher gradients, acceleration gradients than these conventional superconducting cavity approach, which leads to these kilometer-long accelerators. So yeah, in principle, if this can be these plasma-driven acceleration mechanisms, if they can generate sufficiently high spectral flux, I mean, then it is of course an option, yeah. But but the principle has been shown that this type of acceleration works. But the spectral flux and the total photon yield is still comparatively low. If this can be amplified to much higher values, then that could be a way to obtain radiation sources, say on a scale of a lab, yeah. That fits into a lab, and then it will be more compact, yeah. But yeah, so that is the perspective, which is certainly will not yield significant progress in the next years. That will take a while. But until then, I mean, we still need to do a lot of work to further use and further get this resonance ready in a way, for example, that we are able to have single line scandium samples, which are not subject to line broadening, inhomogeneous broadening, and this is the aim of the next experiment, to first of all characterize this, and then go on and develop preparation techniques where the scandium is then really in a single line condition in the solid state matrix. That is the next challenging step, and for that we still need the large scale X-ray lasers.
Yeah, I think it's a very interesting and promising area.
Yeah,
so actually, except scandium, do you have any other candidate to excite?
Not really yet. I mean, theoretically, yes. I mean, the silver 109 that I mentioned and the rhodium 103, they were candidates, but I think this is far from being realistic at the moment, although on paper they have much narrower lines even. But I think it would be too daring, actually, to trying to approach them experimentally in the next years to come. So one should direct all efforts to the scandium, which is really an extremely good candidate to work with in principle, and because it comes very close to the thorium, and then one can also learn all these steps how to prepare this. And if one knows how to get the scandium working, I mean, then from this experience one can maybe go on further to even narrower transitions, like the rhodium or the silver. Yeah, but they have much higher energies. It is a challenge, and so I mean the 12.4, I think KeV is still a spot where one can make good progress in the next years.
Okay, thank you. So do you have any other questions? Let me see.
Doesn't look so, no.
Yes. Okay, maybe it's too close to the holidays.
Yeah.
Yeah. Yes. Okay, if there's no further questions, let's thank Professor Hosbach again. Thank you, Ralph.
Thank you, Zhang Ying.
Okay.
And yeah, it was a pleasure to be in your seminar, and And but maybe next time we can meet in person somewhere, maybe in China when I'm there in November. So and
maybe also in Hamburg.
or if you are in Germany again, let me know. Yeah.
Yeah, I think there will be a conference in August in Hamburg.
Yeah, it's a synchrotron radiation instrumentation conference in
Yes,
end of.
I think I will be there.
Okay, good. Yeah, then let's meet in August.
Yeah, and see you later.
See you. Bye bye. Bye bye.
Bye.